Students, today we will solve one more numerical on beams. This is the question paper from VTU December 2015 and January 2016. In this question paper, if you see question number 7b, here if you see 7b, a uniform cross section beam is fixed at one end and supported by rurals at the other end. Here we can see the support in the other end by the rulers at the at the other end. Okay, a concentrated load 20 kilonewton is applied at the mid length of the beam as shown in the figure. Here Young's modulus is given and moment of inertia is given. We need to determine the deflection under the loading. So what are the deflection we need to determine here? Here if you see in this figure, one end is fixed and other end is fixed by roller support. In the sense we can see this at the end, we can see the moment of the beam in the along the x-axis, whereas vertical moment is restricted by this fixed, whereas horizontal moment we can see because it is supported by rulers. Okay, fine. Now we will start the problem. We will approach how to solve this. Here if you see, the first step of solving beam problem is to modeling and discretization. Since here, as we earlier discussed, wherever there is a point load or any other load, there we need to create a node. Here in this problem there is a point load which is acting exactly mid span, means from 5 meter from the fixed point. So we need to create a node over here. Once we create a node here, the entire cantilever beam becomes two elements. Earlier it was one element, but since the application of node is at the midpoint, we need to create a node. When we create a node here, then the entire cantilever beam becomes two elements. Now we need to calculate stiffness matrix for two elements, and we need to form the global stiffness matrix, then global load vector, global force vector, then we need to apply the boundary condition, then we can get the displacements or deflections under this loading. Here the application of load is 20 kilonewton and length of the beam is 10 meter. The first step is to modeling and discretization. Here, as I earlier said, we have made two elements. The length of the beam is 5 meter plus 5 meter, and we have three nodes, node 1, 2, 3, and in each node we have vertical deflection V1 due to force F1. Here we have V2 due to force F2. Here we have V3 due to force F3. Similarly, we have angular displacement theta 1 due to moment M1, theta 2 due to M2, and angular displacement theta 3 due to M3. So this is how we need to define, like we need to do the modeling over here, modeling as well as discretization. We have discretized the whole element, whole beam element into two elements, and we have modeled, like we have defined the number of nodes as well as the displacement which may occur over here. Once we do this, the next step is to formulate the stiffness matrix. As we know that stiffness matrix for beam element is given by E into I divided by LE cube. LE in the sense length cube, length of the element, E is the Young's modulus, I is moment of inertia, and these elements 12, 6 LE minus 12, 6 LE, 6 LE, 4 LE square minus 6L 2 LE square minus 12, here minus 6 Le 12 minus 6 Le 6 Le 2 Le square minus 6 Le 4 Le square. How to remember this matrix? Since as I already told about this, like this is the symmetry matrix, you need to remember only the upper diagonal elements. If you remember upper diagonal elements, the lower diagonal elements are the same elements. You can see the same elements, and you need to remember the diagonal element, that is 12 4 Le square 12 4 Le square 12 4 Le square 12 4 Le square. See, once you remember this matrix, we need to put the data for the first element. Here, as we know that the Young's modulus is 200 into 10 raised to 3, moment of inertia is 2500 into 10 raised to 4. Here if you see, yes, this is 200 into 10 raised to 3 Newton per mm square. Here 2500 into 10 raised to 4 mm raised to 4. Then we have length is 5 meter. 5 meter is nothing but 5000 mm, so cube. If you simplify this, you will get 40, and we need to substitute the values. 12, here we have 6 Le, here we have 6 Le, 6 into 5000, because length of the element is 5000. If you multiply, you will get 3 into 10 raised to 4. That's what I have written, 3 into 10 raised to 4. Similarly, we need to calculate for the all element by using these. Just we need to multiply the length of the element wherever it is required in this element. Once we do this, the next step is to, here we need to write this 1 2 3 4, because as I earlier said, first element connected between node 1 and 2, and first node has two displacements. Since beam has in beam each node has two displacement, means 2 degree of freedom, that is vertical displacement, and one more is angular displacement. Here again we have vertical displacement v2 and angular displacement theta 2. Here we represent vertical displacement in the upward direction, because upward y direction is positive, and here we have taken clockwise direction because it is positive angular momentum. Clear? Okay. Once we define this 1 2 3 4 1 2 3 4, next step is to determine the stiffness matrix for the second element. Again, second element, if you see these elements, Young's modulus, moment of inertia, and length are same, so if we simplify, we will get this answer. Once we get this answer, the next step is to, we need to substitute the elements. Again, the as we have seen, the same elements, the length of element is same, you will get the same whatever we have in the first stiffness matrix, the same elements will get here. Only the difference is this one, 3 4 5 6 3 4 5 6, because second element is connected between node 2 and 3. Node 2 has two displacement, that is v3 and theta 3, and v2 and theta 2, v4 and theta 4. That's what we will see here. Node 2 has two nodes, and this node has a 2 degree of freedom, that is here v2 and theta 2, and here we have v3 and theta 3. So each node two displacement. As we know, second element, here we have two displacement. First node we already had two displacement 1 and 2, so here we have two displacement 2 and 3. Here we have 4 and 5. Sorry, here we have 3 and 4, here we have 5 and 6. See, this is our whole element 1, element 2, first node, second node, third node. Here we have displacements 1 and 2, here we have 3 and 4, here 5 and 6. Since we are talking about the second element, we have 3 4 5 6. That's what we have written, 3 4 5 6. Once we write this, next step is to form the global stiffness matrix. As I already told in the previous video how to form the global stiffness matrix. Here first we need to write these numbers of rows and columns. Once you write 1 2 3 4 5 6 here, 1 2 3 5 4 5 6 here, Next is to define these elements, like as I already told, first row first column we need to define, next to first row second column, next to first row third column, first row fourth column. Similarly we need to define for all the elements. Once we define all the elements, we will get this matrix. Here 10 raised to 4 as a common for the both the matrix, so there is no need of worrying about this 40. And here we have 6 by 6 matrix because we have 3 nodes and each node has 2 displacements, so we'll get 6 by 6 matrix as the global stiffness matrix. Once you form this global stiffness matrix, then we need to form the global load vector. Global load vector in the sense, here if you see this figure, here we have node 1 2 3, here we have force we have F1 and moment we have M1. Similarly in the second node we have force F2 and moment M2, here F3 M3. So those we have written here, F1 M1 F2 M3 F2 M2 F3 M3. Actually we need to write in the vertical matrix. Here I have written horizontal, so I have written transpose. Now if you see our figure, like there is no force and moment in the node 1, and at node 2 we don't have any what we call any moment. We have only the vertical force that is acting in the negative y direction, so minus 20 into 10 raised to 3 we have taken it as F2 load. That's what you can see over here. Yes, minus 20 into 10 raised to 3, and all other loads are 0 because there is no application of other loads. Once we define the global load vector, next we need to define the global displacement vector. As already told, like each node has 2 displacement, that is v1 theta 1, v2 theta 2, v3 theta 3. This is how we need to define. This is also a what we call column matrix. Here we have written transpose. Once we define these global load vector, global displacement vector, global stiffness matrix, next we need to define this equilibrium equation, where equilibrium equation can be written as k into q, which is equal to f. K is nothing but global stiffness matrix, u is global displacement vector, f is global force vector. Once we define this, the next step is to apply the boundary condition. Here if you see our figure, in this figure, like this is our figure, like in this figure node 1 and 2 is fixed, here node 3 is fixed, means we don't have vertical displacement and we have horizontal, right? Node 1 and 2 fixed and node 3 is fixed, whereas node 4 is movable. The same thing which we have seen here, right? V1, like vertical displacement, for first node we don't have vertical displacement as well as angular displacement. For last node we don't have any vertical displacements, so we need to element 1 2 5. Similarly here 1 2 5. If we eliminate these things, we left out with 40 as a common and 24 0, 3 into 10 raised to 4 0, 20 into 10 raised to 7, 5 into 10 raised to 7, 3 into 10 raised to 4, 5 into 10 raised to 7, 10 into 10 raised to 7, and v2 q2 q3, v2 theta 2 theta 3, minus 20 into 10 raised to 3 0 0. These elements will get, those are written here. Why we have eliminated those things? The elimination approach method tells that wherever the node is fixed, there we need to eliminate corresponding rows and columns of the equilibrium equation. Once we do that, then we get this matrix. Now what we need to do, we need to solve this matrix. If we solve that, we will get the displacements and slopes. v2 is the displacement, theta 2 theta 3 is the angular displacement we will get. How to solve this matrix? So first we need to multiply a row and column which is equal to this one. Next we need to multiply row along with column, next which is equal to 0. Next we need to multiply row and column next, which is equal to 0. If you do so, we'll get the three equation. If you solve three equation, three unknowns by using calculator, you can get there directly the answers. If you see here how we have written 24 into 40 into u2 plus 0 plus 3 into 10 raised to 4 into 40 into theta 3, which is equal to minus 20 into 10 raised to 3. That's what we have written. 24 into 40 into v2 plus 0, 3 into 10 raised to 4 into 40 into theta 3 is equal to minus 20 into 10 raised to 0. Similarly, we need to write for all the 2. Once we write this, if you solve the equations, we'll get v2 theta 2 theta 3. v2 as minus 36.45, theta 2 as minus 3.125 into 10 raised to minus 3 radians, theta 3 as 0.0125. So these are nothing but deflection for the given loading condition. So this is all about the question solution for the question paper. If you have any doubt, comment below so that I can answer your doubts. If you have any demands on any other videos regarding finite element method, let me know, comment below so that I can do a new video on your comments. Thank you for watching. Take care.